Alright, so we started off with ozone depletion. First of all, we stressed the natural order of things. Formation of ozone in the upper atmosphere takes place in the stratosphere when ultraviolet radiation hits the O2 molecules. That splits them apart, and some of them, when they're in their single atom phase, come back together to form ozone, and ozone is very good at absorbing ultraviolet radiation, and therefore that blocks the majority of the ultraviolet radiation from the sun from reaching the ground. So that, of course, is a good thing for us. That's like most of your things that we find in nature. It is helps make the world livable, and that's the way it goes normally. And then, of course, people come in and they add their problems. We make chemicals, these organic compounds that have either chlorine or bromine on them. The number one in that category is these things called CFCs, or chlorofluorocarbons. And when they get up there in the upper atmosphere with the ozone, that same UV radiation tends to knock a chlorine or bromine, depending on the molecule, off of these molecules. And that rogue single chlorine or bromine atom will go around and basically break apart these ozone molecules, and then they'll combine with more oxygen, which will free up that chlorine or bromine atom again, and then it can continue to go along and break up even more ozone molecules. And it's usually on the order of about 1,500 ozone molecules per CFC molecule that can be disrupted and destroyed, and therefore allow ultraviolet radiation to come through, and more of it to come through to hit the surface of the earth, and people and plants and everything. So we also have a occurrence at the South Pole in Antarctica that occurs every year during the months of August or November, basically their spring, our fall, where because of the weather conditions, both the temperature and the polar vortex and all that kind of stuff, the ozone depletion is very significant, down to about 5% of normal. Now, in other parts of the world, its depletion goes upwards of 50% in some areas they measure, but usually it's ranging 70 to 80%. I'm sorry, 20 to 30% of how much it's depleted by, leaving 70 to 80%. Let me make sure you understand that. So with this one, with the ozone hole over Antarctica, or the ozone thinning over Antarctica, it goes down to 5% of what it normally would be. So it depletes by 95%. Okay. But anyway, that happens. It's been called the ozone hole, although it's not completely correct, because it's not an actual hole, and just know what it is, where it is, and when it happens every year. Fortunately, we've been able to get a handle somewhat on the problem of these ozone-depleting chemicals being in the atmosphere by nations coming together and agreeing on, the majority of the industrialized world agreeing on stopping the manufacturing and distribution of these particular substances, controlling them from going into the environment. For example, we strictly monitor if you throw your refrigerator away, for example. They will treat it very specifically. You have to ask them to come out and get it. You can't just put it by the roadside and expect the garbage company to pick it up. Somebody else might, but and so when they take it to landfill and everything, they take it off to the side and suction the freon out of it if it's older. And freon's a primary CFC that's been used in the past. And then I think they incinerate it or burn it, but they keep it from getting released out in the atmosphere. So it is strictly controlled. It's been phased out. These substances, the CFC substances, have been phased out of your major applications, such as aerosols and refrigerants. And therefore, meteorologists believe that basically the influence of these CFCs in the environment has reached its peak, because it takes a little while, because they stay up there for a while. Has reached its peak, and the level of these should be declining in the near future, and therefore the ozone layer itself should be recovering somewhat, and eventually back to its full state as these things precipitate out of the atmosphere. So what happens because of this ozone depletion is basically extra UV radiation, and UV radiation is particularly toxic to microorganisms and in particular plants. So the number one plant type microorganism is phytoplankton, and so they have actually been shown to have suffered from this. But in general, it has more of a negative impact on plants because plants are designed, the chlorophyll in them is designed to absorb radiation and in the visible light range. This extra UV radiation, everything just kind of blows apart that chlorophyll molecule, and therefore the plant can't, obviously can't make food and stuff. So we're pretty familiar with the effects on people of extra UV radiation, i.e. sunburn, which then of course can lead to skin cancer. Cataracts is another thing that your body does to help to shield itself from excess UV radiation. So those would you expect with less ozone to be more of a occurrence of these particular symptoms. And then also, of course, because that UV radiation does damage plants, it's going to damage crops, and that's always going to be a negative effect human health-wise. And that's pretty much it for ozone depletion. We didn't go into a huge amount of detail on it, but I covered the areas that typically are covered on the national exam. So any questions about that phenomenon? Okay. Notice I didn't say anything in there about temperature. Also didn't say anything in there about CO2, because those particular subjects are in the category of global warming, global climate change, okay, which we're going to next. I do want to make sure everybody has a clear division between those two. That's ozone there. And then we got, I think, there we go. Global warming. So we start off with the natural way, just like I did before. How does it naturally work in nature? What do we do to mess it up? What can the effects of it from that? What can we do to fix things? So when it comes to global warming, global climate change, the natural phenomenon that's being affected, or is believed to be affected, is the greenhouse effect. And that is the property of our atmosphere, the certain gases in our atmosphere, what we call greenhouse gases, to be able to trap reflected radiation, which, by the way, tends to be in the infrared range. Didn't really stress that, but that is something that you should know. That's another difference. You've got UV radiation that is blocked and absorbed by the ozone layer, but these greenhouse gases are absorbing and in a way blocking the reflected infrared radiation from leaving the Earth's atmosphere and going out into space. To an extent, we always have to have some of the energy eventually transmitted back out, but under normal conditions and everything, that's what we have. That makes our atmosphere a good 60 degrees Fahrenheit or 30 degrees Celsius warmer than normal, and therefore, of course, does a great deal towards making the Earth more habitable. The problem is that we are putting out a lot more of these greenhouse gases, particularly CO2 in the atmosphere, and we climatologists are concerned with if we're not increasing this particular effect to the negative, in a dangerous way, if you will. So we know that CO2 is a greenhouse gas. You can theorize that if you increase it, you're going to increase the temperature of the Earth, like adding extra blankets, you could say. But research has been done to try to verify the data, because you can't, of course, set it up in a laboratory. And we find that through looking at ice cores and other things, that we find a direct relationship between CO2 and temperature from the past, meaning where we had CO2 levels were high, temperatures tended to be high, and where CO2 levels were low, temperatures tend to be low as well. So pretty good evidence of the factor that having more CO2 in the atmosphere could be raising the temperature of the Earth. So what would be the problem with that? Several things. Of course, sea levels are going to be most direct things. Sea level increases that would happen from melting ice going into the water, raising the level there. You would see, particularly in the tropics and stuff, species that cannot adapt to that hotter weather. They don't really have anywhere to go that will be cooler. By the way, because they're not adapted, they need that rainfall and everything. So they're kind of stuck there, and so they tend to believe that you're going to see more loss of diversity in the tropical areas. And in other areas, ones where there are temperate zones, you would tend to see movement of populations towards the polar regions. So they may lose out in the more temperate regions, but they could gain as they move towards the polar regions more so. the certain things like pest populations, mosquitoes, etc., or other things that are do better in warmer, wetter climates, which you would see in general overall. Many of which are like our pests, are things like mosquitoes and stuff, and therefore spread of disease and also spread of damage to crops from these organisms is something that you could anticipate. Just general change in weather patterns overall. Increased flooding would be pretty much the norm worldwide because we'd have more water in the system. Some areas you would see more drought, and you would theoretically see in some areas more severe storms because of there being more energy behind those storms, increased temperature. What else? Decreased dissolved oxygen levels in aquatic ecosystems. Warmer water does not hold gases as well, and oxygen is one of those gases that would come out from that. Meltwater from ice changing the salinity of ocean currents may disrupt those particular patterns, and those can have an effect, of course. They have major effects. Ocean currents, as we know, have major effects on climates, so disrupting that can have unforeseen circumstances. And also because of these different weather conditions that would cause from it, you can expect crop failure, failure of livestock as well. You can add that in there. That, of course, is going to be a human health issue for that because of that. So the unfortunate thing about studying this particular phenomenon is we don't know for sure exactly what type of things will happen, and some things are going to happen in some areas and some things are overall. So I guess if you wanted to sum up what would happen, stuff would change. You know, some places get water, some places get drier, etc. Some, mostly warmer, but some places, because of like ocean currents and stuff, make it colder. Some species will thrive, some species will drop back. And we do see, I think it's a pretty good guess that some of the species that are going to thrive, these pest populations, that's going to be a negative impact, of course, on human health and stuff. All right, any questions on that slide? Okay. So there's your diagram of the natural phenomenon of the greenhouse effect and the potential if with added greenhouse gases of how it could be more of an effect. Notice the main difference between these two, besides, as you can see here, extra greenhouse gases in here. More heat escapes into space, less heat escapes into space, and therefore the overall Earth would tend to get warmer under that scenario. All right, ice core samples. So there's our graph showing the direct relationship between temperature on the top and CO2 and temperature in blue, and CO2 in green. Don't worry about the dust thing right there, besides the fact that you should know, by the way, you should know that dust overall will tend to cause the climate to cool. And we have direct evidence of that. But there you have it. So there's definitely a direct relationship. Not completely clear yet, however, whether or not that is the temperature leading the CO2 or vice versa. And we talked about briefly how if it gets the Earth gets warmer for other reasons or because of the greenhouse effect, that it tends to release CO2 in the atmosphere from the ocean because, once again, gases do not dissolve as well in warmer waters. Just like we said, you would find drops in dissolved oxygen levels in aquatic ecosystems. You could also expect to see the CO2 dropping from the ocean, which means it's going to go into the atmosphere. And that, therefore, you'd have an increase in CO2 in the atmosphere. Yeah, this is an overall graph over the past 60 years, basically, of CO2 levels. And also the zigzag pattern shows how there's a seasonal change in CO2 levels because of the change of the seasons and the fact that the northern hemisphere has more trees and terrestrial plants, and therefore in the summer in the northern hemisphere, for us, CO2 levels tend to drop as those trees absorb much of it out of the atmosphere. And this, make sure you know this particular table used to be green. But just your main greenhouse gases, those four, the strength of them, and where they come from. Kind of went into these already. I don't think I need to repeat myself on them. But there you have that. Make sure you're clear on that. And then this one you don't have to know in particular. It's just for kind of an FYI thing, but it does show you some of the potential, some of the predicted potentials of sea level rise, and where that sea level rise will be coming from. First, starting with the thermal expansion of the ocean is just getting bigger, And then with glaciers and ice sheets melting as you get warmer, that's what you can expect to see as far as the sea level going up. All right, and then finally we looked at positive and negative feedback mechanisms. Positive ones being ones that the initial effect, i.e. an increase in temperature, will cause something that will cause even more increase in temperature. So we looked at several examples there. One most common, snowpack, more or less ice because it's warmer. Ice reflects, making the earth cooler. Therefore, less ice means less reflection, means the earth is warmer, and therefore even more ice melts, and so on and so on. It keeps going. And then methane hydrates, methane trapped in ice. It gets warmer, that ice melts, releases methane in the atmosphere. Methane is a greenhouse gas, making it warmer still, and then even melts even more of the permafrost or perhaps on the continental shelf, and that releases even more methane in the atmosphere. And then what we just talked about with the CO2 in the ocean, it gets warmer, the water in the ocean gets warmer, it releases more CO2 in the atmosphere, that causing it to get warmer still. On the negative side is, which means good, because it's counteracting it. So this is so we don't see a runaway effect here. The CO2, increased CO2, and increased temperature and water available in longer growing seasons, that kind of thing, will increase tree growth. Trees are the best way to pull CO2 out of the atmosphere, and so those things will help to set it back in the opposite direction. And you could see one effect, actually one way or the other, as far as cloud cover. Some clouds are good because they reflect the sunlight, but other clouds are actually against that because they act like a greenhouse gas in that they let the radiation through, but then they trap it on the way back out. So it's really on how dense the clouds are. And you can see this on a sunny day, where you see clouds and they're white because the sunlight's coming through it, but when those clouds build up, then of course it turns gray and black because the sunlight can't make it through it. In that case, the sun's actually being reflected back off into space, and they will tend to cool off the surface of the Earth. Okay. All right, so what can we do about it? The biggest thing, of course, is reduction of the burning of fossil fuels and biomass, in particular trees. Because of course that's what releases CO2 in the atmosphere in the first place. You're taking carbon that's been stored away either in the ground in the case of fossil fuels or in the trees, the biomass of trees themselves, and you're putting it back out in the atmosphere where it can add the greenhouse effect. Carbon sequestering is actively capturing that CO2. The best way to do that, once again, trees, that's a biological sequestering. They naturally pull that CO2 out of the atmosphere. And you notice I'm saying trees rather than just plants in general, because trees, of course, grow and they get bigger and bigger year after year, whereas most of your other plants and stuff, they either are annual plants, so they grow and die within a year, so they're going to just decompose, release the CO2, or they get eaten, or they just grow to a smaller size and really don't continue to grow year after year like shrubs and things, and therefore they're not storing away that CO2. Chemically, there's some scenarios that could be done where you react the CO2 in the atmosphere with calcium oxide in a solution, makes calcium carbonate that sinks out. Physically, capturing the CO2 as it's directly produced, maybe from a factory or something like that, from a power plant, and then storing it away somewhere. I don't think that's got a lot of potential, but that's another type way to do it. Like I said, once again, the main thing is planting trees. Of course, with trees also, you get so many other things: habitat, food source, soil stabilization, and so therefore you just can't really lose when it comes to planting a tree, unless, of course, you plant a tree that's an invasive species, and we'll talk about it later. All right, cap and trade. Make sure you understand this particular concept. This is the one where the government sets a cap, the maximum amount of a particular substance, in this case is carbon dioxide, that companies can put into the atmosphere. And then the government, if a company that normally produces carbon dioxide is under that cap, that limit, the government will actually issue credits to that company, which can be used by other companies to reduce their amount that they put out, and therefore get them under the cap so they don't get a penalty. The reason why this tends to work is that it encourages the fuel efficient company, or maybe a solar company or something like that, an alternative energy company. It automatically gives them a revenue stream, an ability to profit right off the bat by selling these extra credits to the power companies. So they automatically got a customer there. They don't have to wait to build out there, to get individual people and stuff signed on and things like that to start making some money. So that's the big incentive part of that. So it does incentivize technology and people going into alternative energy and things like that. And then finally we have the Kyoto Protocol. This is another attempt, at least, like the Montreal and Copenhagen protocols, which were actually quite successful at reducing the ozone depleting chemicals in the atmosphere. This one is the same goal when it comes to carbon dioxide emissions and other greenhouse gases, and has not been nearly as successful because it's really just a much more difficult problem to handle. It's much more common and widespread that CO2 is put out anytime you burn any kind of fossil fuel, so that means pretty much everybody is a CO2 emitter, where it's only a small industry that used your ozone depleting chemicals. Then there's not really an alternative. There's alternative energy, of course, but is still under development. The alternatives for the ozone depleting chemicals were actually quite similar chemicals that were developed quickly and had actually been around already. So that's just a comparison of why one particular protocol was much more successful than the other one. And also one of the criticisms of the Kyoto Protocol is that it does exempt developing countries, and at present that includes China and India, and China has already surpassed us as far as greenhouse gas emissions, and I'm sure India is pretty close. So there you have it. Any questions about those? No? Okay, I'm going to go ahead and